All right, as we begin today, let's go ahead and turn your textbooks to page 291. Hopefully you did well on your test. Students in here did fairly well for the most part. Some little things here and there, but overall I was pleased, felt like students did well. I want to just review some things with you very quickly, and then I'm going to show you a new approach to something we've already done that we're going to need for next year in Algebra II, and of course for the final exam coming up in another week or so. Look at exercise, or problem number 1 there on page 291. It gives us the square root of 9/64. Now remember, anytime you have a fraction inside the radicand, there's really only one thing you truly care about, class, and that is the denominator. You have to take the root of the denominator. Can you take the square root of 64, class? Sure. What do we get? 8. Now, do I care about taking the square root of the numerator? Generally speaking, no. But if you can, of course you would, right? So we'd go ahead and take the square root of 9 also and just get 3/8. Look at exercise number 3. They give us the square root of 3/25. Well, again, the only thing I really care about, class, is the denominator. We have to take the root of the denominator, but can you take the square root of 25, Maddie? Yeah, of course you can. What do you get? 5. Can we take the square root of 3, go 2 for 2? No. So what do we do? Just leave the square root of 3. Because you took care of the denominator, remember that's the most important part. So as we look at exercise number 6 now, we have the cube root of 4/3. Well, again, the thing we care about, Brecken, is the denominator. We have to take, in this case, the cube root of the denominator. But, Noah, can we take the cube root of 3? This time, no. So remember we said we're going to make it happen, right? What number, Noah, do we wish were right here? Because then we could take the cube root of it. 27, right? Is it the smallest cube on our cube list that 3 can become? 3 can't become an 8, and the next smallest number is 27, so there we go. So to make it become a 27, of course, Noah, we said we'd multiply top and bottom by. Now I want to specify something for you. Pay close attention here. Technically, when you multiply the 9, it is under the radical here that you're multiplying a 9. Because can you multiply, class, a 9 times the square root or cube root of 4? No. A rational 9 could not multiply by a cube root of 4. It's technically a cube root of 9 that gets multiplied by the cube root of 4. Does that make sense? So it's kind of like the 9 is under the radical, and there's a reason I'm emphasizing this to you. Okay, now for sake of ease, I just said, well, just multiply by 9. But we do understand, since you have to have the same index to multiply, and you can't multiply rational by irrational, technically they were cube roots of 9 that were being multiplied to give us what fraction, Noah? 36/27. Then, of course, we could finish it out by taking the cube root of the denominator. And can I do anything? Maybe even reduce the cube root of 36? 8 doesn't go in, 27 doesn't go in, and then 64 is already bigger by far, so we'll just leave the cube root of 36. This is stuff we've done already, right? But I want to show you some things we haven't looked at. Look at number 7. Copy it down on your paper. 20 over the square root of 7. We haven't seen it in this fashion, in this form before. So we've worked with fractions and radicals and taken the root of the denominator. We've never done it where the denominator is a separate radical all by itself. Do you see that? It's always been numerator, denominator, or one full radical. Now, you don't really have a fraction in the radical. You have a radical in the denominator. Does that make sense? It's not a denominator that happens to be within the radical, but rather a radical that is in the denominator. This is no good. Just as this is no good, you can't have a denominator inside a radical, you can't have a radical inside a denominator. Never the twain shall meet. They just don't get together, okay? They hate each other. Or at least we hate both of them. I don't know. Anyway, you cannot have that. So we have to do something called, if you write this in your notes, rationalizing, or I want to say rationalize, because it saves me 2 letters and I'm lazy. Rationalize the denominator. Rationalize the denominator. Rationalize means to make rational, right? For instance, if you're arguing with someone who believes that the moon is made of green cheese and you're trying to educate them and help them understand, no, it's just a big worthless rock up there that we don't You know, other than helping with tides and stuff and seasons, you know, that's why God put it there. But, you know, you try to rationalize, you try to help them think rationally about something. Never mind, I'm not going to go there. But anyway, try to help them think rationally. Rationalize the denominator means we make it rational. And just like before, the premise was you have to take the root. You know what you have to do to rationalize the denominator? Take the root. And again, it's only the denominator we care about. We care nothing about the numerator, other than making sure it's simplified, but it's the denominator we key in on. So question, can I take the square root of 7, class? Nope. So just like before, we're going to make it work. Brecken, I could do something about that if instead of a square root of 7, it were, say, a square root of 49. Now, he could have said square root of 4, and he would have been right, but I can't make a 7 turn into a 4, or a 9, or a 16, or a 25, or a 36, but I can turn into a 49. So what I really wish were right here, right, is a square root of 49. Now question, how do I turn a square root of 7 into a square root of 49? Well, I'd multiply it, but not technically by 7, right? Technically, if I multiply the square root of 7 by 7, I get 7 times the square root of 7, don't I? Technically, Bracken, you multiply the square root of 7 by the square root of 7. You multiply it by itself, essentially. Now, not always does it have to be multiplied by itself. For instance, if we had, say, 5 over the square root of 12. Well, I don't have to multiply by square root of 12 to make this rational, right? What could I turn the square root of 12 into, class? Well, you're right. Actually, I could reduce this down, I suppose, but I would just want to make it rational. What about the square root of 36? Right? That would still come out rationally here in just a moment. So here I would multiply the square root of 12, class, by, not by 3, that'd be 3 square root of 12, but by the square root of 3, right? So again, I don't always have to multiply something by itself to get a rational denominator, but in this case I do. But we know this, class, what you do to the bottom, do to the top. So I'm also going to multiply the top by the square root of 7. So we said square root of 7, square root of 7, square root of 49. 20 times the square root of 7, class, gives me what? Bingo, 20 times the square root of 7, right? Don't overthink that. And so the numerator is just this whatever, right? 20 times the square root of 7. But I don't care about the numerator. The point is I can take the root of the denominator, class, and now get 7. Can I cancel the 7 with the square root of 7? No, again, one's rational, one's irrational. We don't mix the two. But notice now I have rationalized the denominator. The denominator is now a rational number. Does that make sense? So looking here, we said we have the square root of 12. Well, I can't take the square root of 12, but I could take the square root of 36. So we multiply top and bottom by square root of 3. Square root of 12 times the square root of 3, square root of 36. What about 5 times the square root of 3, class? Yeah, 5 times the square root of 3. What would my answer be here, Maddie? Good. 5 times the square root of 3 over 6. Do we see what we're doing? It's very similar to what we did before. The only difference is we have to remember the radical symbol as well. Before we just kind of said, well, we multiply top and bottom by 9. Well, technically we didn't, but that's how we thought of it, right? Here I'm emphasizing don't multiply top and bottom by 7, but by square root of 7. We're good to go? Let's take a look at a couple more. Look at number 8. 5 over the square root of 3. And Noah, what do we need to do to rationalize the denominator?
Take the root.
Take the root. But I can't take the square root of 3, Noah, so what do I do? All right, so that my denominator becomes, but we don't just multiply the bottom. What we do to the bottom, we have to do to the top. So we'll also multiply the numerator by to get, and then I'll simplify my answer to get, and there we go. Seemed like a pretty easy concept given what we already learned earlier. Just kind of building on that idea. Let's look at number 11, and we've got 6 over the square root of 48. Now, in my thinking, I'm like, hey, square root of 48, I could reduce that, right? 16 times 3, pull out of 4. Whoa, whoa, whoa. I don't want to reduce it. I want to do what, class? Take the root. That's what's got to happen. I've got to take the root. So simplifying it down doesn't do me no good. I've got to turn the 48 into something else. Now, I will throw this thought out there. If you reduce it down, it may make it easier to take the root. I'm going to show both ways. But method number one, what can I turn 48 into? I don't know either, right? Well, I do because I'm the math teacher, but I'm like, I look at that number, I'm like, I don't know. So here's an approach, class. Try multiplying it by 2 and just see what happens. What's 48 times 2? 96. Can I take the square root of 96? No. So multiplying by 2 doesn't do me no good. Okay, let's try another number. 3. What happens if I multiply it by 3?
144.
Does that help me? Yes, okay. So in some cases, when the number's just obnoxious, right, just think, well, what could I multiply it by? Does 3 help? Now, I wouldn't multiply it by a 4, because that's already a square, right? But I might multiply by a 5, 6, 7, 8, not 9, 10, and so forth, right? Or you go back to Old Faithful, right? You make the list, though I'm not sure how effective this method would be for you in this case, since you're trying to blow something up into something. I don't know if even writing 144, you would think of it, honestly. So I don't know that the list helps you that much, which is why I generally just think times 2, nope, times 3, oh, good. And if it's like, no, times 3, nope, okay, how about times 5, how about times 6, and then just go from there. But yeah, we want to turn this into the square root of, what was it again, Noah? 144, by doing what, Brecken? Good. I like that you didn't say multiply by 3, but by the square root of 3. And of course, what we do to the bottom, Maddie? So we're also going to multiply the top by the square root of 3 to get what? And what do we get when we simplify down here, Maddie? All right, good. Questions, comments on this one? Good, Gavin. We can reduce the fraction, can't we? Yeah. Gavin didn't say it either, but I'm giving him credit for it. Yeah, we can reduce, right? 6 and 12 could reduce here because they're both rational values to get what, Maddie? Good, the square root of 3 over 2. We cancel to get a 1 and 2. So actually, there's our final answer. Right? Now, that's one way to do it. Remember I mentioned at the beginning, though, we might be looking at the 48, hey, I can reduce that. And I said, technically, that's not the objective, right? But it might help make the objective easier. For instance, if we saw 16 times 3, then I could take the square root of the 16 to get 4 times the square root of 3, all underneath the 6. You follow what I just did? Just took the original problem and reduced. Now, the reason this can be helpful is that now I'm not trying to rationalize a big old square root of 48, just a square root of 3. What can the square root of 3 turn into, class? Square root of 9, right? If I multiply top and bottom both by square root of 3. So in my numerator now, Brecken, I would get, careful here, in the denominator I would get, Noah, well, initially 4 times the square root of 9. Let's go and show the in-between steps for the sake of the video, which is 4 times 3, which is 12, right? So again, I think making a 3 into a 9 is a whole lot more mentally simple than making a 48 turn into a 144. Technically, you still just multiply by square root of 3, right? But here I think it was easier to see, so it may help you to reduce first, okay? That said, if you're lazy and really smart and can think through times 2 and times 3 and times 5 and times 6 in your head really quickly, this method takes less steps, but that may actually be mentally easier for you. Questions on that problem? Let's take a look at a couple more here before I have you work some on your own. Number 13. Number 13, we have a 2 times the square root of 2 over the square root of 3. Here we have a radical in the numerator and a radical in the denominator. But the only one I care about, class, is the one in the denominator. What do I need to do? Walk me through the process here, Maddie. We multiply top and bottom by square root of 3 to initially get, Maddie, which then obviously simplifies into, all right, y'all following just what Maddie was doing there? right there with her. How about number 15 here? We've got a 4 times the cube root of 5 over a cube root of 16. Now, there's a couple directions you could go here. I'm curious to see what you'll do here, Brecken.
The denominator, make it 8 times 2.
All right, Brecken's looking at this like, I don't want to turn the 16, which is a decent sized number, into something even bigger. Let me factor it down into 8 times 2 so that my denominator then becomes 2 times the cube root of 2. So let me come over here a little bit here. My problem now is 4 times the cube root of 5, and in the denominator we've turned it all into a 2 times the cube root of 2. Now, thoughts here real quick, Brecken, even besides the radical for just a minute. I can actually reduce the 4 and 2, can't I? If I wanted to, I could do that now. I don't see a reason not to. That becomes a, and that becomes a 1, which I don't even care about, so I'm just going to cross it out, right? So now my focus is solely on a cube root of 2 instead of on a cube root of 16. Thoughts on the cube root of 2? Good. We want to turn it into a cube root of 8, so we multiply by a cube root of 4. And what we do to the bottom, so my numerator is also going to change. 2 times the cube root of 20. And now? All right, so we get 2 times the cube root of 20, and the cube root of 8, of course, is just plain old 2. And my answer is just, and 8 doesn't go in, and of course 27 doesn't go in, so I leave my answer just like that. There's another option we could have taken. I'm going to go back to what we originally had. Nothing wrong at all with what Brecken did here. But the more conventional approach would be to say, well, I can't take the cube root of 16, but I could blow it up into a 64. How would I make a 16 turn into a 64 class? Multiply by 4, or in this case, technically, the cube root of 4, right? Notice here, then, that's going to give me 4 times the cube root of 20 all over the cube root of 64. But, of course, we know the cube root of 64 class is 4. Gotta know these, is 4. And then, whoop, and notice I do this much work instead of, well, I actually did the initial step over there and then here and all of that, right? It's just a little bit less work. So if you can see the 64, it's quicker to go this way. But there's absolutely nothing wrong with doing it the way Brecken did. We arrived at the correct answer, and we didn't have to deal with big numbers. And maybe for you, fewer steps written isn't as important as little numbers. Okay? Questions on this before you try some on your own? All right, so I'm going to have you do, here on page 291, numbers 2, 4, 5, 9, 12, and 16. 2, 4, 5, 9, 12, and 16. Rationalizing the denominators. For the sake of time, go to put your pencils down. Check your answers to the first 4. I felt these were very straightforward, especially the first one. It can't get easier than that, right? It's already rational, 12/5. For the next one, at least the denominator you can take already, just the numerator. On the next one here, 6 doesn't turn into 8, or 27, or 64, or 125, but obviously 6 can turn into 6 cubed, which is 216. Just need to multiply by 2 more 6's. In other words, 36. To get 36 2/16, which gives you the square root of 36 over plain old 6. We good to go on the first 3 problems. These are like what we've done before the test even. Ooh, questions? Did you treat like a square root and just multiply by 6? What happened?
I skipped it.
You skipped it, slob. Do you understand what you should have done?
I multiplied by 4.
Can you take the cube root of 24 though?
But then I made it like 8 times the cube root of 36.
Oh, interesting. Okay, let me follow this line of thought. Brett can multiply by 4 to get 4 24ths, which gave him the cube root of 4 over the cube root of 24, which, since it factors in 8 times 3, can give him the cube root of 4 over 2 times the cube root of 3. And then you could hopefully see the 27. So maybe multiply by a cube root of 9, and that would give you the cube root of 36 all over 2 times the cube root of 27, which is 2 times 3, which is 6. So in theory, if you followed that train far enough down the track, you would have actually gotten to the correct answer. I think it's a little quicker just to get to 216, but I mean, it works, right? That's the main thing. All right, the next one I think was very straightforward, very similar to what we've just been doing there. Do we get 7 squared root of 10 over 10? And then we come to the next one, 68. That's ghastly, right? I don't even know how to, well, I do because I'm a math teacher, but if I'm a 9th grader, I don't even know how to reduce the square. I don't even know if it does reduce. You know, if it does, it's 4 times 17. But since we didn't learn our 17 times tables, we didn't know that. So we try the other method. What is 68 times 2? Should have already done this. What's 168 times 2? Okay, 136. Does that help? No. Okay, so times 3. What do we get? 204. Does that help? No. We're not going to waste our time multiplying by 4. How about times 5? $340. Does that help? No. Times 6. $408. This is still not working here. Times 7? $476. This is not, I'm almost out of numbers, right? Because we only memorized up to 20 squared is 400. Okay, so apparently on this one, when you start getting beyond what you've memorized, I guess we're going to have to figure out a way to reduce it down, kind of like Brecken did with the 24 thing here. So here we would have to figure out, I guess, 4 times 17, and take the square root of 4 to get 2. So with 10 over 2 times the square root of 17, and that's why. Look what we're going to have to multiply top and bottom by, class. Square root of 17. So, I don't know, with that one at least, the only real, I mean, we were going to take forever multiplying if we try to get our way up to 17, right? So here, 10 times the square root of 17 over 2 times the square root of 289, which of course we already know is 17, gives us 10 times the square root of 17 over 34. We can do a little reducing there though. Take out a 2 to get 5 and 17, so 5 times the square root of 17 over 17. By the way, might have been easier to reduce the 10 and 2 here and save ourselves the time and trouble. But yeah, that one's just, frankly, kind of evil. Really evil, especially to 9th graders. I'm not quite sure why they did that. Do we understand how to do it, though? Okay. Do we understand at some point you got to give up on the times 2 times 3 times 5 method? Like Once you get past 400, you don't have it memorized anyway. Even if you had a square, you would know you had it, right? So don't go too long there. That told me, okay, we need to switch to this method. I think this last one's a little bit more straightforward. What do we need to multiply top and bottom by on this last one here, Brecken? Well, cube root of 3, there we go. Multiply top and bottom by a cube root of 3 to get what initial answer? All right, and then what, Maddie? And can we reduce anything? No, we can't even reduce the cube root of 18 because 8 doesn't go in and obviously 27 doesn't go in, so we're out of cubes. And there we go. All right, yeah, number 12 is just evil. All right, questions on that one? Questions on those? All right, look at number 17. Go and copy that one down. And we see something interesting in 17 that we really haven't worked with much, that you'll work more with in Algebra 2, and that's letters. We've worked primarily with numbers. I think once you understand letters, though, they're easier. All right, just like with reducing radicals, when you get to the letters, it's just how many times does this go into that, right? Well, similar thing here with the denominator. We've got the square root of a over b. And again, the only thing I care about is the denominator. Can I take the square root of b? That is, does 2 go into 1, class? No. What can 2 go into? 2. What else can it go into? 4, 6, 8, 10. All those numbers, right? But it can't go into 1. What we want to do is get the smallest number that's still bigger than 1, which of course, class, is 2. So what I want to have is a b squared, because then the 2 can go into the 2. But in order to turn a b into a b squared, class, I need to multiply by another square root of b. And what we do to the bottom, do to the top, so my numerator becomes ab. Because this is already a square root of a times the square root of b gives me the square root of ab, right? Which is why I just said b over b in the past when it was all under one big radical. And so I cannot take the square root of ab, but I don't care. I take the square root of b squared, class, to get just b. Go to finish that out at your seats as well. Then go over to number 19. Now this one has a letter, but it's not in the denominator, so I don't care. Because remember, all I care about is the denominator. 5th root of 2. You can't take the 5th root. You can't take any root of 2. What's the smallest thing we can take the 5th root of, class? 32. Can a 2 become a 32? Sure. You multiply top and bottom under the radical, of course, by 16, 2 to the 4th, right? Because we have 1 2 here. We need 4 more 2s, 16, to get the 5th root. And so that'll give me what new fraction temporarily here, class? You have 48x over the 32, which leaves me the 5th root of 48x all over 2. And there's my answer for that one. Notice we just kind of ignore the letter because it wasn't in the denominator. All I care about are denominators. 27. We have the 4th root of 7 over 2y squared. Well, 2 problems. Number 1, I can't take the 4th root of 2. Problem number 2, 4 doesn't go into 2. What can 4 go into, class? 4. How would I make that a y to the 4th instead of a y squared? Multiply by another y squared. So that here in just a minute, I've got a y to the 4th, right? Of course, we know what we do to the bottom, y to the top. So I also have to multiply a y squared to the top here in just a minute. All right, but the 2 is also a problem. I can't take the 4th root of 2. What can I take the 4th root of? 16. So I'd have to multiply top and bottom also by, still under the radical, 8. So that my denominator becomes the 16y to the 4th that I need. Do you see how to work with numbers and letters simultaneously? As far as the numerator, of course, class, that just becomes a 56y squared. And I can't do a thing with the square root of 56y squared, but I can take the 4th root of 16y to the 4th to get, class.
2y squared.
2y to the first is 2y, right? Write this down if you would. Now, all of those have been single fractions under the radical, but we can do the same thing with something like this, where the radical is only in the denominator. Same approach, class. I can't take the cube root of m, but I can take the cube root of m cubed, or m to the 6th, or m to the 9th, or m to the 12th, and so forth. But why would I make my life harder than it has to be? So I want to turn this into the cube root of m cubed. How do I go from a cube root of m to a cube root of m cubed, class? Multiply by, but technically not m squared, but by the cube root of m squared, correct? And so also in the numerator, what you do the bottom, better do the top. The numerator we also multiply, class, by the cube root of m squared to get 2 times the cube root of m squared. My numerator's ugly, but there's nothing I can do about it, and frankly, I don't care. In the denominator, though, I can take the cube root of m cubed, class, m. Write this one down, though. Very similar problem. 2 over the cube root of m to the 7th. Can I take the cube root of m to the 7th evenly? You say, well, we could reduce it, right? 3 goes into 7 2 times with 1 left over. I don't care. I want to take it evenly. What can 3 go into evenly? 3, but that's too little. 6, that's too little. 9, right? So if this were the cube root of m to the 9th, I could do it, right? Do you see how to take the next biggest number that can work evenly? Obviously, to make this happen, once again, class, we need to multiply top and bottom by the cube root of m squared. And of course, the numerator will again be, but I can take the root of the denominator, and the cube root of m to the 9th just becomes m cubed. Do we see how to work with letters when they're bigger than the existing power? It's so much quicker to do it this way than to try to reduce it down. Stay with me, I want to show you 2 more. What about this? 1 over the cube root of m to the 11th. What do I want the denominator to be this time? Someone besides Noah. What can 3 go into evenly? 3, too little. 6, too little. 9, too little. 12, there we go. So if I can make this a cube root of m to the 12th, I'd be good, right? What do I multiply top and bottom by? Cube root of m. And so I get the cube root of m over the cube root of m to the 12th. I don't care about the numerator, leave the cube root of m, but I can take the cube root of m to the 12th to get m to the 4th. One more example before I give you your homework. Write this down. 1 over the 4th root of m to the 11th n to the 5th. I can't take the 4th root of m to the 11th. I can't take the 4th root of n to the 5th. What do I need to do with the m? What do I need to make it become, Maddie? M to the 12th. What do I need to do with the n, Noah? I just saw what I did there. I wasn't even playing. M for Maddie and n for Noah. Anyway, all right, go ahead. I'm easily amused. N cubed would give me an n to the 8. That's the goal, right? The target is a 12 and an 8 because 4 can go into those numbers. So we need to multiply top and bottom by the 4th root of, class, m and n cubed. And of course, 1 times anything is itself, so we'll just keep the 4th root of m n cubed in the numerator, and you can't do anything with it, which is fine. The denominator comes out evenly now, though, class 2. N squared, m cubed, n squared. Do we see what we're doing here with the letters? Your homework for this evening is to do page 291. You got just 5 problems for homework, so a shorter assignment. You do have some exams I know we're getting ready for, geared up for. Page 291, numbers 10, 14, 18, 20, and 21. Page 291, numbers 10, 14, 18, 20, and 21. And we'll take a look at those tomorrow. Then there's one last idea with this rationalizing denominators we need to talk about tomorrow, and then we'll begin our review in the next lesson following that. Have a wonderful rest of your day, and you are dismissed.